Okay, so I think everything's working and recording. I can't tell. There it is. All right. Off we go. So, yeah, let's pick up where we left off. Let's talk about some newer stuff closer to the end of the semester than from last time. So let's talk about searching. That was a big thing. We learned how to do a few searching algorithms through arrays or vectors. And so just the idea of searching in general, right, is when you're looking for something inside of some bigger thing. There are many other data structures that you could want to search through, like maybe a linked list, for example, but we talked about this in the context of vectors and arrays. So, like, here's your array. With linear search, linear search works for any kind of array. So that's the first one we learned about. 3, 9, it's always, you got some array, you got some vector. And you'd like to figure out, you'd like to know where a value is. You're looking for some number. Say you're looking for 3. So for linear search, you have no guarantee about where your number 3 is, right, in your vector. So you just got to search from left to right until you find it. And then, oh, cool, we found it. And the name of the game is, if you find something, you give back its index. That's what we care about if we're searching through an array or a vector usually. Otherwise, if you're looking for like a value like 42, you go and you try every possible index, and if it's not there, you return back to the user. You're always supposed to return an index. You return an invalid index. You return -1 if you don't find the thing. So, yeah, that's that. Linear search will always find what you're looking for because it has to search through every value, right? It'll eventually find it one way or another. So it doesn't matter what the array or the vector looks like. Linear search will do the job, but it's kind of slow. It's not nearly as fast as binary search, so we would prefer to use binary search to search through our arrays or vectors for stuff if we can. And we can only use binary search, though, when we have a sorted array. All right? So, yeah, let's say, like for this one, you have some number that you're trying to search for linear search. Like maybe the number we're looking for was 3, and we find it, we give back the index of the 3. Or if the number we're looking for was 42, we give back -1. Okay, so that's that example. And now for the other one, we need like a sorted array for binary search. 0, 3, 5, 6, 7, 8, 9, I guess. So I've sorted that. So if you are given a sorted vector or an array, you can do it much faster. You can play that guessing game. All right. So if you're looking for, let's say you're looking for the number 8 in a sorted array. And so you can use binary search. How does that work? You set up your search space, right? Your search space is initially the entire vector because you haven't looked through it yet. But you start in the middle of your search space always. So you look at the 6. You just look at one thing. And you compare that to what you're looking for. And you notice that it's bigger. So immediately, right, you can cut off this part of the array because you know that everything to the left of 6 is totally smaller than 6. So you know that if that 8 is anywhere, it's over here. You've cut off half the array, and you can do that every time. Now you have a smaller search space that you can search through, and you can go through the middle of that. And immediately, like you notice that the middle is 8, which is what you're looking for. And so you can immediately return and you're done. But, yeah, so you only took like two checks in the array to go and find this 8, which is way over here. So that's pretty nice. You just keep updating your search space. Like if you're searching for 9, you'd be like, okay, I chopped that off. Now I'm looking over here. And eventually you'll find it in the middle of your search space. Or if you're looking for 10, eventually your low and your high indices will pass each other. And that will tell you that it's not there. So those are your options, okay? So just by the fact that you know, like once you look somewhere, you know that everything to the right is bigger, everything to the left is smaller, or equal to, I guess, technically. But that lets you cut off half of your search space every time. It's wonderful. And let's code it up after I draw some examples. So let's say we have a vector that holds 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. And let's say we're looking for the number 2 in this vector. Let's spell out like how we got to code this. Because I don't want you to memorize it. Because I know it tells you how to do it in your book. And I know I've given you the code before. But I want you to understand what's really going on here. All right, so at the very beginning, what we do is we set up our search space. We have a low index and a high index. It's the whole thing. Because we haven't seen anything yet. And we're looking for the number 2. Okay. And then we look and we find the middle of our current search space. This is a loop. So there's our mid index. It's 0, 1, it's 2. Index 2. So we go there. We go and we look at our mid, we compare it to our 2, and we notice that, oh, the thing that we're looking for is smaller. All right? So that means we can chop off. We don't need to go ever to the right anymore. We can chop off that part of the array, and the only rest of the array that we need to look through is the 2 and the 4. So up to index 1, and that involves changing our high index. Low can stay the same. For all we know, the 2 could have been at index 0, and it really is eventually. But that's what you do first. Okay? And then, so that means high is changed. Let's see if I can copy all this easily. That works. And so high is going to change. High is going to become, boop. Let's see, what else can I do? Don't need that. High is going to go over here. So now low looks like this and high looks like this. In the next round of our loop, we have this search space. Okay? And so still, we're looking for 2. And so we calculate the midpoint. What's the middle index between 0 and 1? What's the average of 0 and 1? With integer division, it becomes 0. And so mid ends up being index 0. And we notice that, hey, that's what we were looking for. So we can immediately return index 0. So we're done. So that's pretty nice. That's how it works. That's how binary search works. You just do this in a loop, and your search space eventually shrinks. Let's pretend we were looking for something that's not there. Let's say that our number that we were looking for instead was 1. We'd still get to the same spot, right? We'd still get here. Mid would give us 0. Oh no, 2 versus 1, it's smaller. So that means, again, when you find something that's smaller, just like this one, you're going to change your high index. So that's going to move our high index to index -1, and that's going to pass the low index, and low and high should be in that order. So the second that happens, then your search space has been exhausted, you have run out of places to look, and you didn't find the thing. So if low and high ever pass each other, then you're done, and that is it's going to be the condition of our loop. All right, so let's code up binary search so that we remember it, and that will be that. And I'll do it on vectors. So I'll include the vector library. And so here's my vector v, 2, 4, 6, 8, 10. And we will do binary search on v for the number 2 first. It'll be there, and then the number 1 after that, it won't be there. All right, so int binary search, because it's got to return an index if it finds it, -1 if it doesn't. Going through a vector that I don't want to copy, but I want memory savings, so const reference. And then val to search for is what I've been calling this. All right, so we got to set up our search space. That's what we got to do. Set up our search space to be the low index is 0 and the high index is our size -1, just the whole darn thing. Search space is initially the entire vector. And so we got int low equals 0, int high is v.size -1. So there's that. And then while low and high make sense, so while low is less than or equal to high, they're still like in order. If they ever pass each other, we didn't find it. But as long as they're normal, then I have a real valid search space to go through. And the name of the game is always go in the middle, look at that thing. All right. So look at the middle index. Int, what's our middle index? It's low plus high over 2. All right, there's another way to do this that you'll learn about in an algorithms class, but let's just do it this way because our indices will be small. And so we compare the thing at index mid to the value that we're looking for. That's what we do. All right, you got a couple options. Either it's bigger or smaller or just right. So either way, we can cut off half of our search space. All right, so let's look in the middle, compare what we see there to what we're looking for. All right, so if we're in this case, like the thing I see is bigger, so if the value I'm looking for is bigger, the value I'm looking for is smaller than the thing I see at the midpoint of my current search space, so val to search for is less than v at mid. That's this case that I drew here. If that's true, that means we need to look to the left. We need to, like the highest index where it ever could be was index mid -1. All right, so we're going to move high to here, like we did. look to the left, which involves moving our high index. It's mid minus 1, because we just looked at mid. We don't have to make it mid or anything. We know it's not mid either. So it's strictly less than. Otherwise, if the value I'm looking for is bigger than what I see, be at mid. So I'm looking for, like, I don't know, let's say I'm looking for 42 and I see 6. Then obviously I better look to the right of that. And so the highest index is still fine, but the lowest index where I could find the thing is mid plus 1. So that's looking to the right. That means change your low index. Make it more to the right side. Low equals mid plus 1. That's the lowest place where you could find it because it wasn't mid. All right. Otherwise, if it wasn't less than and it wasn't greater than, it was just right, and we found it. And so our goal, remember, don't lose sight of the task at hand. Our goal is to return the index where we find this thing. So we just found its index. It's at index mid if it's equal to. All right. And so that's while we have a normal search space to go through. Eventually, if we don't find it, if it's not there, high and low will pass each other, and this will become false, and that will stop our loop. So if we ever get outside of this loop, we return -1, because that means we didn't find it. Sad face. All right, so that's binary search. Hopefully that's coming back to us. So let's compile and run that, and that'll be it. So there's that, and we get our 0 and -1. Any questions about that? Just shout out if you have any. Yeah, that's our first example of the day. Let us next talk about the wonderful thing that is recursion. So in recursion, if you have a recursive problem that you're given, that means you can find a smaller version of that problem inside of itself and use that to help you solve the bigger original problem. Okay? So, a good first example was like factorial or something to the power of some integer thing. So let's do power calculation. That's recursive. So like let's write out some examples and notice that. It's like x to the 5th power, no matter what it is, like that's x 5 times, right? X times x times x times x times x. Do you see a smaller power computation inside of this bigger power computation? Sure. There's a few of them, but you're usually looking for the next smaller one. So there's x to the 4th, okay? So generalizing this, do you see how x to some arbitrary integer n is equal to, just pretend, it's equal to that x times x to the n minus 1? And what do you know? There's a smaller power computation. That's recursion. There's a recursive case, okay? And then we have to worry about a base case, like when is the answer so small that this recursive case stops making sense? A good stopping condition for n is 0. Anything to the 0th power is 1. Go back to our original recursion slides if you want to see the justification for why that's a good stopping point. But that is that's what we came up with. So this is our recursive case. So for some general n, this is how you give back the answer for x to the nth power. And then otherwise, if your power is 0, anything to the 0th power is 1, just immediately give that back. So let's make a file for that. And let's call it somewhere. Where do I want to call it? Am I turning this into a library? Of course I am. I'll do that later. Let's see. Here's how I want to use this. So I'll be like, cout pow. The x part, that could be a double. That's fine. But the power itself needs to be an integer. So I can be like 2.0 to the 5th power. That's totally fine. So that's the kind of thing I want to do. And so let's make this pow function now. Double pow. It takes some, I'm calling the thing x, and then n is the power. Double x int n. So this is going to return x to the nth power. Let's see here. So we got to determine, are we in the base case or are we in the recursive case? We have two different things to do, depending. So if n is 0, that's the power, right? We're taking something to the 0th power. Anything to the 0th power is 1, except for maybe 0 itself. And there's your base case. Okay? Otherwise, if we're not in that one, hopefully we got a positive power. You can probably check for that and return an exception or throw an exception if you need to, but let's just trust the user. Otherwise, let's assume we're in the recursive case. And in that case, we need to give back, right, x to the nth power is equal to x times x to the n minus 1, or x to the n minus 1th power, excuse me. And so how do we give that back? We say return our x times, how do you give back x to the n minus 1th power? Well, that's us. That's our job to compute it. And it's a smaller problem, so you get to assume that calling yourself pow x n minus 1 will correctly give really back to you the answer to x to the n minus 1th power. And so you just get to trust in the magic of recursion to do that for you. And as long as you build up the answer correctly and have a good base case, it really will work. And so what's 2 to the 5th power? Is that 32? 2, 4, 8, 16? Yeah, 32. We get our 32, and it's beautiful. All right. So I encourage you to draw the stack, like figure out how this is all working. Go back to the recursion lecture if this is fuzzy. But that is our first example of recursion. That's a review. For my second example, let me give you something that you haven't seen before. Binary search, in fact, you can do without a loop. You can do recursively. That's kind of cool because something's getting smaller every time you're searching, right? It's the search space itself that's getting smaller. The distance between low and high, that's getting closer and closer to 0, isn't it? Every time you start making guesses and cutting off half your search space. So in that case, we could make a binary search function where low and high are our parameters, because then when we call it, it will be getting smaller. Low and high will be getting smaller. We get to assume that it's going to do the right thing and solve our search problem. Isn't that so fun? So binary search, you can do it recursively, and I want to show that to you. So let's steal, let's include vector. And so I'm going to steal all of my binary search stuff. Let's do this one. This is the iterative version, right? That's the adjective you use with things that aren't recursive, things that use loops. This is the iterative binary search. I'll steal that for a second. Then also let's steal the example runs that we did too. So like these guys. These guys. And then we're going to call it differently as well. But we also need to make a vector, excuse me. So let's do that. Here's our vector. Cool. So let's translate this into a recursive binary search. It's going to be so cool. So, all right, first of all, binary search needs more parameters. It needs the search space as parameters. So low and high become parameters to binary search. So here, do that. Int low, int high. Those are parameters to our binary search. And then now we need to call it like that. So what's the initial search space? It's always 0 for low and size minus 1 for high. So that's going to be, oops, where do I want to go? I'll just say v.size minus 1 like that. Good enough. And so that needs to go here too. Low is 0, high is v.size minus 1. So I'm passing those bounds, my search space, to the initial call to binary search. All right? That's the only thing you need to change on the user's end. And so now when we implement it, we're going to get rid of this loop. It's going to be so cool. All right? So we have to think about base cases and recursive cases because the search space is getting smaller and smaller and smaller. So when do you have nothing to look through and you can immediately give back an answer? That would be your base case of binary search. That's when you have no search space. When your search space is empty, you're done. There's nothing to do. You didn't find it. That's your base case. Does that make sense? So if low is bigger than high, that's your base case of a recursive binary search. Your search space is empty. Return -1 immediately. Otherwise, if we're still here, I'm going to get rid of this loop, right? We don't need a loop anymore. Don't need this anymore. Don't need that indentation anymore. Interesting. The rest, like if we didn't return, we're in the recursive case. So otherwise, we're in the recursive case where we have a non-empty search space to look through. Might be of size 1, who knows? But what do you do? What do you do in binary search? And the recursion will just fall out of it. This is our recursive case. So we look in the midpoint, right? V at mid. And so if the midpoint, if the thing that we're seeing at the midpoint, if that's bigger than the thing we're looking for, if the thing we're looking for is smaller than the thing we see at the midpoint, alternatively, we look to the left. What does that mean for us recursively? Binary search to the left. So instead of setting high like this, we're going to say binary search on V for the same value, right? With the same low, but the new high is this. The new high is mid minus 1. See? Sorry, mid minus 1. That is what you do if you need to look to the left. Recursively, just let it do that. It will find it. If it's there, return -1 if it's not. And whatever this result is, that's our full final result too. We're going to return that back. Because this is the smaller call. We get to assume it's going to find the thing if it's there, or return -1 if it's not. And what do we want to return as the original call to binary search, the bigger call? It's just either the index if we found it, or -1 if it's not there. So just return what the smaller call gives us. That's the answer. Same for looking to the right. If we want to look to the right, if the thing we're looking for is bigger, that means return binary search with the same high index, same upper index, but the lower index is changing to mid plus 1. And so that's the argument, right? That's the low argument we give it as low plus 1. That's looking to the right. That will successfully, you just get to assume, using recursion, it will search for the thing in the right half of the vector, give back the index if it's there, or -1 if it's not there. And our job is, for the original call, for the bigger call, is to do what they did. Give back that same answer. Return it. They did all the work for us. Cool. Otherwise, if you found it, then we finally have the answer on our hands. We don't have to do any recursion, like we found the thing. Okay? And that's recursive binary search. That's legitimately it. You call it with the initial search space. The search space becomes the parameters, part of the parameters. So those are your arguments now, low and high. You add those as parameters. And then your base case is empty search space. You're done. Recursive case is you have a valid search space to look through. Go and look in the middle. And then either recurse left to search left, or recurse right to search right, if that thing wasn't at the middle. Otherwise, if you found it, you're done. Okay? Isn't that beautiful? You're gonna have to stare at this, I think. But it's so cool that binary search is recursive. I don't think you thought of it that way before, but it really is. And it's gonna find the thing. Boop. You get index. We're looking for 2. Index is 0. Yeah. Looking for 1? Yeah, it's not there. -1. Cool. Yay. So that's binary search, and that is those are my 2 examples of recursion for the day. Again, just yell at me if you have questions, but I think the next thing that I want to do is makefile stuff. So, there we go. Let's talk about makefiles. That was a way to automate the compilation process, make it easier on ourselves, and also allows us to do separate compilation very easily. So, remember the stages, right? Zooming in. Remember the stages. So compilation, just the word compilation means take a single source file, like one CPP file, and turn it into machine code, your ones and zeros. And then linking is what combines them. Okay, so let's think about it that way. Remember this diagram. So you have your .cpp file, your C++ program. Then you feed that to the compiler. The compiler is the thing that gives machine code for that one file. That's object code. G++-C is our compiler, and that spits out a .o file. Right? You might have to do that for a bunch of times because you might have a bunch of individual .cpp files. Right? That's separate compilation is doing that. And so you have a bunch of .o files eventually. Like you have some more, or you have like pre-compiled object code, like your IOStream library that we always like to include, or like your vector library, all that fun stuff. That's sitting to the side, and then it's the linker's job. The linker is also G++ for us. It's kind of confusing. And then it's the linker's job to bring those all together into one final executable file that you can then go and run. That's like your ./recursion. And when you give a bunch of files to G++, it'll do this for you. But we'd like finer grained control so that we can do separate compilation. Right? Separate compilation is when you do those .o files and you explicitly make them with the G++-C. So let me show you that. Let's translate our recursion file into a recursion library. So the functions will be declared in a header file, implemented in an implementation file, and then we'll have a separate file for the main function that uses our library. And then we'll make a make file that builds the stuff. All right, I'll talk about separate compilation first, though. So let's take this file that we made, all beautiful, and split it up. So let's make a recursion.h file. Remember your header file guards. And then I'm going to take the declarations of these guys. POW and binary search. Those will be declared in our implementation file, or in our header file. And so this needs the vector library. You are not allowed to use namespace standard in a header file, so standard : vector all day long. And then recursion.cpp is the corresponding implementation file, which it will include the header file, include recursion.h, and it's allowed to use namespace standard all day long, that's fine. And then the main file will go in a separate place as well. So the main function will make a new file, boop, and delete that from there. I'll call it main.cpp, let's say. And this will include IOStream, and then it will also include our recursion.h file, which will include vector for us, which is nice, and then give us access to our stuff, and then using namespace standard is totally fine in any implementation file, because nobody's going to copy and paste that. All right, so I got a bunch of files now. I've got recursion.h, header file, recursion.cpp, implementation of everything I promised to implement in the header file. Then main.cpp has the use, like I'm using my library, I'm including it, I'm doing my stuff with it. And so separate compilation is the idea of compiling it this way, all right? You have your recursion.cpp, and then you have your main.cpp. You are going to compile those separately. This is the compilation process. Compile them separately into recursion.o and main.o. I need more room, sorry. This will be recursion.o. This will be main.o. And then once you have those, you'll link them together with the linker into a final executable file that you can then go and run. We'll call that recursion. There we are. That's good enough. And so let's do that manually first. How do you do this just on the terminal? Let me remove all the compiler files. Let me remove the recursion file. Let's use separate compilation. Let's be like, all right, here are all my files, right? Let me show this all to you. We have implementation file. We have header file. We have main.cpp that includes and uses our stuff. All those things are coexisting. And so to do separate compilation, I'm going to say g++-c on both CPP files, recursion.cpp, and then also main.cpp. And that will generate .o files, object code for both of those. You can't run them yet. You got to link them first. So then we run the linker, g++ is just the linker, and then you give it both .o files. Oh, zoom. You give it main.o and recursion.o, and then you can have it called whatever you want. We'll call it recursion. And so that's the three-step process, essentially. And it's going to work exactly the same as before. But you go through this intermediate stage so that, like, when you change main.cpp, you don't have to, like, recompile recursion.cpp. That separate compilation is good for that. All right? It does become a lot if you do this manually, though. All right? So the answer is make files. A make file is just a little, it's like a cookbook. It tells G++ how to build all your stuff. And if you want to do separate compilation, that is just, you can bake that into the rules. So you got a bunch of targets, which have a bunch of requirements that they need. And then you give the body of the rule after you tab over. So let's make our make file that does exactly all this. Let me remove all the compiled files. We'll do it all over again. Let's go here. I'll make a new file called makefile with a capital M. And what I want to do in a makefile is have rules for all the things I would like to make, all the intermediate steps as well. So I want to make main.o. I need a rule for that. That's its name. And usually the name of the rule, the target, is the file you're trying to create. From main.o, what do I require in order to make main.o? Well, main.cpp better exists somewhere. That's my one requirement. And then how do I use that ingredient, that requirement thing, to make main.o? How do I use main.cpp to make main.o? I use g++ -c. Okay, so there's that one. Same for recursion. Recursion.o requires recursion.cpp to exist, and then to make recursion.o from it, you use g++ -c again. And then usually you put the rule you really care about at the top, so you don't have to give it a name, so that you don't have to use the name when you say make on the terminal. But all right, the final thing I want is an executable file called just recursion, and to make it, I require main.o and recursion.o. Okay, those need to exist, and the beauty of make is that it will make those things if they do not yet exist. And then what do I need to do to build recursion from those two things? I need to link them together with g++. So g++, give them both, -o, give it, be called recursion. Okay, so that's my makefile. And notice right now I don't have any of that. I have, well, the makefile exists now. I don't have any .o files. I don't have what I want. So I can say make main.o if I wanted to make those things separately. And so that'll go and find the rule and run it and make main.o. Let me remove that. Back to square one. Or I can say make recursion. Hit enter. It will notice those .o files don't exist, so it will go off and run those rules. You see it running those intermediate rules? And now it's like, all right, now I have the things I need. I'll build what you really wanted. So that's very powerful. That's really cool. Now it exists. You can run it. All the .o files have been made for us. And also, if you put the rule that you really care about at the top of the file, you don't have to say make recursion. You can just say make, and that will run the first rule. It's really cool, really nice. And then the beauty of make files plus separate compilation, which we baked into these rules, is that if I make a change to one of these files, I don't have to recompile the other one. And if you have a million source files, which you will one day, then this is going to save you a lot of time. So let's search for, I don't know, let's search for the 8 this time, somewhere over on the other side of the vector. So I've made a change to main.cpp, and the make file will notice that. If I say make again, or make recursion, it will notice that main.o is not up to date. It will notice that recursion.o is fine, but main.o is not up to date. And so you see it running the rule to remake main.o because it noticed oh yeah, the time changed. The modification time of the file changed. It's like, all right, I'm going to make this now. So it remakes main.o, does not remake recursion.o, and then it goes and it links things. So you saved a lot of time like that, only recompiling what really needed to be recompiled. I didn't touch the recursion library. And so now I can rerun that file, and I get my new output. Cool. Any questions about that? All right. I also think I said some stuff about this in our little cheat sheet. So if you go to our last lecture, got some cheat sheet stuff. Feel free to look at all that. It's pretty much saying what I said before. So we had recursion, right? What you want to do with recursion is write out some concrete example and then find the smaller problem, the one smaller problem inside of it usually. There it is. And then generalize the example into a recursive case, just like this is the factorial example. And then try out that recursive case until it stops making sense. That becomes your base case, and rinse and repeat. So that's recursion. Then make files, we just talked about that. So here's the setup, all these things, and so here's just some helpful information about make files. Remember the tab, and yeah, just read that if you're interested. That's me trying to help you. So I think the next thing that I want to talk about is bitwise stuff, so I'll stay right there. Cool. So yeah, let's do bitwise operations now, because that is using ints to do not math. Using numbers to store individual bits and mess with individual bits. All right, so every int is 32 bits long, so it's a nice compact way to put 32 bools if you need them. All right? So bitwise operations are going to perform our standard logical operations, those things that use truth tables like and, or, and not, all those things, on the bits of numbers, usually two numbers. Not takes a single number and it just flips all the bits, but every other bitwise operation takes two numbers and it like lines them up and it does stuff with the corresponding bits. Okay, so let's see here. Remember that every int is 32 bits long, so like you have some long int, you can access which bits. There's a numbering to the bits that we talked about, right? The rightmost bit is bit 0, then it's bit 1, bit 2, bit 3, all the way to bit 30 and 31, right? Because you started at 0. There's 32 bits. The highest bit is 31 for your ints if you're using an int. And so yeah, let's do some practice with bitwise operations, and that'll be that. Let's see, how do I want to do this? So I have some examples eventually, but let me draw some stuff. So you got your and, your or, your not, your exclusive or, your shift. Say like and, for example. And is good for checking if a bit is set. So let's give an example at least of that. So let's say this is your number. I'll write it out in binary. Obviously, if this was an int, it would have a bunch more zeros this way, but you don't really think of them like that. So let's say that I really wanted to know if this bit of this number was set. To figure that out, I can bitwise AND it with a number with only that bit set. Zeros everywhere else, okay? And then I would know if this particular bit of the original number was set based on whether the result is, because everything else is a 0, because the AND is going to force a 0 everywhere. If there is a 1 here, that means it really was set. If there was a 0 here, if this was a 0, it would produce a 0 here and the whole thing would be 0. So you just check if the output was 0 or not, and that would tell you if the answer was a 0. Okay? So that's that one. Bitwise OR, I think you can understand. OR is good for setting a bit. You OR with a 1 in the bit that you want set. That'll work for you. Exclusive OR is good for flipping bits, right? You can just flip, and I guess I have an example of that soon, but you can flip bits like this. Like you have a 0, you can exclusive OR that with a 1, and now it becomes a 1. And then if you have a 1, you exclusive OR that with a 1 again, and it will flip it back to 0. So that's what exclusive OR is good for. And so with that in mind, let's make some examples using bitwise operations. Let's make a multiply by 2 to the n function that takes a number and multiplies it by 2 to the n using a shift, which is going to move over a number. And then we'll do a flip bit function as well. So I'll see if I can copy both of these. Sometimes PowerPoint's unhappy about that. But yeah, like here are your bitwise operations. Hopefully you kind of see how they're going to work. You're just going to align them, and like and does that, or puts a 1 if there is a 1 anywhere. And then exclusive OR is like gives a 1 if they're different, a 0 if they're the same. Okay. So there, and then not flips them all. And then shifting to the left at least, adds zeros on the right. So like moves things over and it's going to multiply. So yeah, just look at that if you're interested. Bitwise.cpp. That. And then there's this. Yeah, of course it messed it up. Good job, PowerPoint. Like puts weird space characters for no good reason. So multiply, this is going to do int. This is going to be int. So I guess the first one I want to do is make a multiply by 2 to the n function. So the way that I want to use it is like this. Multiply by 2 to the n. You give it an initial number like 3, and let's say we want to multiply it by 2 to the 4th power. Make it giant. All right? So that's how I want to do. I want to do essentially the point of this is to do 3 times 2 to the 4th power. That's how I want to call the function and use it like that. So that's 3 times 2, 4, 8, 16, whatever that is going to be. That's how it's going to work. And so we can implement this function, this multiply by 2 to the n function, using shifts, because shifting multiplies by power 2, doesn't it? So if I say multiply by 2 to the n 3 and 4, so if x is 3 and n is 4, x is 3, n is 4, what do I got to do? I want to produce 3 times 2 to the 4th power, which is 3 times 16, which is apparently 48. I did that ahead of time. And the way you do that is you shift, all right? So 3 in binary is 1, 1. If you shift that just once, that will produce 1, 1, 0 in binary, which is 6, right? That's 4 plus 2. That's 6. Interesting. All right, what happens if you do it twice? If you left shift that twice, then that will produce 1, 1, 0. It'll bring in 2 zeros. 1, 1, 0, 0, which is 8 plus 4. That's 12 now. Do you see the pattern? Remember the pattern? So if you shift left by 1, it's essentially multiplying by 2 to the first power. If you shift left by 2, it's multiplying by 2 squared to the second power, multiplying it by 4. So if I want to multiply by 2 to the fourth power, I want to shift left by 4. So this is a one-liner, return x shifted left by n. And that'll do it. And there's my 48, yay. Okay, so that's that one. And then one last one that's a little complicated. I think I had you think about this in lecture once. Let's make a flip bit function that takes a number and which bit we want to flip, and it'll flip it. So let's say that we give it this initial number, 1101, which is 13, I guess. Wait, is it 13? 1, 1, 2, 4, 8. Yeah, 13. Let's say I want to flip this bit number. This is bit number 1, by the way. All right, bit number 1 of the number. What you do is you can use exclusive OR for that. Exclusive OR for flipping. So what you do is you flip it with a 1 in the position you care about flipping, and then a 0 everywhere else. Oops. And then a 0 everywhere else. And if you do bitwise exclusive OR, see what's going to happen. It's going to preserve everything else. The zeros will preserve things. And then this guy, if they're different, it will flip it and make it a 1. And so that's how you can flip it. And then you can do the same thing on the new value, the 1, 1, 1, 1. Now it's 15, right? If I want to flip it again, you can just exclusive OR with the same number and watch how it's going to preserve everything. And then now they're the same, so it's going to unset it. It's going to toggle it. It's going to flip whatever was there. And so the way that you get at which bit you want to flip, the easy way, like this is your exclusive ORing with the number 2. How do you figure out that it's 2? It is, you just take 1 and left shift it by 1. That's your bit. Left shift it by which bit. That'll get you a 1 in that bit position, which is what you cared about. So that, therefore, is this. So what do I give back? Return Rx, exclusive ORed by a number with a 1 in that bit position that I wanted to flip. Boop. So just like that. That will toggle that bit right there. And, oops, impressive that I used brackets rather than curly braces. But now it seems to be happy. And now let's call that. Let's be like, this was the number 13. This example was the number 13 originally. It will create 15. And then this was 15. It should put it back to 13. And somehow I managed to do it wrong. That should be a 1 there. There. Alright, so cout, the result of flipping the bit of the number 13, flipping the bit number 1 of 13. That should create 15, and then flipping the first bit of 15 again should bring it back to 13. So there's all that. What else? What else? Yeah, I think that's happy. So that's the output we should see, and then, yeah, cool. It's making 15 out of 13 and 13 out of 15 by doing that flipping. Any questions about that one? Alright, so, yeah, all that we have left to do is exceptions. I think there's a page about that. So exceptions are about catching and throwing stuff, right? When something bad happens, so the person who discovers the bad thing throws a runtime exception or some sort of, just any object or any number, any piece of data, you can throw it as an exception. And when you discover the error, that's where you throw it. But somebody else, somewhere outside of that, right? You could have used an if statement otherwise. Somewhere far away from that call, from that noticing the error, they should try catch, right? The try block is for code that might throw an exception, and then you put a bunch of catch blocks attached to it for every exception that you want to handle right there that you know how. All right, a catch block is like, I know how to do this thing. I know how to handle a runtime error exception. I know how to handle this other kind of exception. And customarily, you catch it by reference, and the reason for that has to do with inheritance. But we won't deal with that in this class. But yeah, just remember to catch it by reference. You'll never run into trouble. And then runtime error and other standard library exceptions have a .what method, which is cute. It just gives you back a string that tells you what went wrong. So that's exceptions in a nutshell. But yeah, exceptions are meant to signal exceptional things that like you want to fix and deal with. Oops, where was I? There. Standard except is where runtime error exists and all that. Runtime error's constructor takes a string. But yeah, in general, you have a try block where you put a bunch of code that might throw an exception, and then you put a catch block, as many as you need, that like takes the type of that exception by reference, give it a name if you want to use it, and you, in the body of that, you handle the exception, you handle the problem. The second the exception happens, it will jump out of the try block. It won't continue any code later. It'll go straight to the corresponding catch block that's closest. All right. So I have a couple examples of this. Let's steal some of our code. Let's steal our recursive power function. Let's steal our flip bit function, because those could go wrong, can't they? All right. So let's take both of those, and I'll explain why they could go wrong. So new file. Exceptions.cpp. If I want to throw exceptions, I need standard except if I want to do those kinds of exceptions, at least. Did I spell that right? I hope. And then strings. I'll use strings in the parameters of things. So let me steal my power function, pow, recursive. And then, oops. Oh man, that's what I get for not saving it. Oh no, I did. Cool. There's pow. And then let's do flip bit as well. I will steal that, because actually these functions, the user could mess up. So pow, you can mess up and get into an infinite loop if you're given a negative power, right? Like it'll never get down to 0 because it's already less than 0. It'll be like, all right, what's x to the negative first power? Well, it's x times x to the negative second power, x to the negative third power. We'll just keep on hitting this case. Do we see that? So we don't want to have that happen. So this function should not be allowed to handle a negative power. So in this function, we should notice, like, if our n is ever less than 0, that was the user's fault. This is not going to work. Throw a runtime error, let's say. And the constructor for a runtime error takes a string and gives some description of what went wrong. Can't take a number to a negative power. You can yell as much as you want at the user, but it's you throw the exception when you find it, but you don't immediately handle it. Like you let the person who called you incorrectly handle it. That's the whole point of exceptions. Let somebody somewhere down the line deal with it. And then flip bit could also go wrong because like the only bits that you can flip of an int are 0 to 31. These are like tells you to flip bit 32 or bit -5. We should also yell at the user. Okay, so if they gave us a bad bit number, if which bit is less than 0 or it's like bigger than 31, it's invalid. So let's throw a string for fun. Throw whatever you want. Throw invalid bit. And there's a reason I'm using the string constructor here. If I did this, if I threw this, that actually is a C string, surprisingly. Just the syntax, it creates a C string. It's been up-converted to a string whenever you assign to a string, but I'm not assigning to a string. So I need to throw it to the string constructor. So now you know. So that is, again, we're noticing the problem here, but we should be dealing with it when we call these things. All right? So the idea is like sometimes pow is going to work. See out pow 2.5 to the 5th power, I don't know. Sometimes it'll work just fine. But other times, we're going to do it wrong. All right, 2.5 to the negative 5th power. And so now we're going to notice that, and we will not have it just blow up. Because right now I'm not catching it. So it's going to blow up and it's going to be like, oh, runtime error. But the first one worked. So the way you do this right is you make a try catch. You say try. Inside the tries body, you put all the stuff that might throw an exception. And then you catch any kind of exception that could have been thrown here by reference. Runtime error, reference E. And then like you handle the exception somehow. Maybe you ask the user to enter a new power or whatever. But I'll just print E.what, which gives back the string. So that'll fix that one. And now it's like running to completion properly. So there's that. And then also you got your flip bits, right? See out flip bit of 15 and 1. We did that one, right? That's fine. 15 negative 1. That's never going to work, right? So again, that's going to throw an exception. It's going to throw a string exception. We need to catch it because otherwise it's going to stop the program with a runtime error. We don't like that. So again, try catch. I need 2 separate try catches, by the way, if I want to run this code. Because if I put this code up here, if I did it up here, remember that a try catch stops the second the first exception occurs. We're always going to throw an exception right here, so we will never get to these lines. So they got to be in a different one. Or just to spell it out, if I do this as well, I will never get to this call to flip bit, right? Because I'm giving it a negative bit before that. It will go straight to the handler, and then that's it. Catch string reference S, C out S, new line. So there's that. Okay, and then we're handling it. So remember, the second the exception occurs, we jump to a handler. So like this one's going to work, but then this one threw that exception. It noticed up here, it's like invalid bit throws the string. We caught that string as it jumps straight here, and it prints out the string, and we never run this line. Do we see that? That's what try catch does. It's like it bails out the second something went wrong. It's your job as the programmer to come back to this code if you really need it to do this line too. So you got to write it in a different way if you want that to happen. Okay. So yeah, that's exceptions in a nutshell. Any questions about this? Again, there is no point of trying and catching in the same function where you throw. Let me just make that incredibly clear, because obviously you could have just used an if statement like printed something here, right, if that's really what you wanted. But no, the whole point of an exception is to notice the problem somewhere far away from where you handle the problem. That's the goal of exceptions. It lets you have a disconnect between those two things. Maybe several function calls outside, you can fix the problem where you have the context of how to fix it, how to fix it. So yeah, I think that's what I wanted to say about exceptions. I think that took us through the whole cheat sheet. Yeah, so with that, we made it. You guys did it. Thank you for putting up with me. And all that I really have to say, other than asking you if you have any questions, is good luck on the final. Remember that it's in this class during the final time. So yeah, I believe in you. And then also, before you all head out, let's just take a moment to thank Robert this semester for helping us all a whole lot, I think, right? So thank you, Robert. We love you. But yeah, that's all that I have for us. Stick around if you have questions, but I will stop the recording now.